All right, the first thing we're going to talk about is section 5 of chapter 4, L'Hopital's rule. 4 indeterminate forms. Indeterminate comes in 3 forms. When a function is indeterminate, it comes in 3 forms. Okay, first off, it's got to be rational functions first. This only works for rational equations. F of x over g of x, where g of x is not equal to 0. When we say something's indeterminate, that means it has no finite answer. The 3 forms indeterminate is you can have 0 over 0. You can have infinity over infinity. Infinity over 0 or 0 over infinity. As long as your numerator and denominator are not finite fixed numbers, constants, we can apply L'Hopital's rule. So what L'Hopital's rule says is this. We have a function, we have 2 functions. Let f of x and g of x be 2 continuous and differentiable functions on an, so do I have to open or closed? Or does it matter? Well, on a closed interval AB. Let's look at that. So the polynomial function P of x is the quotient of those 2 functions. Is f of a equals f of c equals g of c if they equal 0 at some point in the domain. Then we can use this rule. Because what it's saying here is this: if this is true, if f of c equals g of c equals 0, then we take the limit of this, it equals 0 over 0.
So it meets one of the conditions or one of the
forms, right?
forms. Yeah, one of the forms.
Because that means it's indeterminate. What L'Hopital's rule says, if this is true, in algebraic, we did begin the semester, if we have 0 over 0, that means there's something in common with both of those functions. And we could algebraically remove it. But what this is saying is that x approaches c of f of x, g of x, then that thing is we can take the derivatives of both the top and the bottom separately. At some value. And as long as we keep on getting 0/0, we can keep on taking the derivatives of the functions until either the top or the bottom is no longer 0. Okay, so that's the beautiful thing about the L'Hopital's rule. As long as you have 0/0 or infinity over infinity or any combinations, we can keep on doing the derivatives of top and bottom separately. Note, this is important. You're not doing a quotient rule here. It's not the derivative of the function. It's the derivative of top and bottom separately.
Hmm.
These are not the same thing. So don't take the quotient rule. Just take the top, take a derivative of it, take the bottom, take a derivative of it, and then take the limit of it and see if it works.
And once you do that, are
And
you
then I'm gonna go ahead.
are you basically finding like the derivative of the function f of x over g of x if it works?
I mean, if we take both of these and they work, is it the same as finding this? Is that
Yeah.
what you're asking? No, it's not.
Okay.
Because doing this, we have to use the quotient rule, which is the the g times f prime minus f g prime divided by g squared.
Right.
This is just f prime over g prime, nothing.
Okay. Okay.
So yeah, it's much more simple than the quotient rule.
Right.
All right, so let's look at examples here. Example one. I'm gonna actually I had to try to put this thing up online before class, so it's easier if anybody's at home to watch it. But we're gonna do example one. The following limits involve 0/0. So we put 0 in there, 3 times 0 is 0, sine of 0 is 0, so top is 0 over 0, so that's 0/0. 1 plus 0 is square root of 1 is 1, minus 1 is 0 over 0, so that one. So all of these 4 conditions apply for, they're all 0/0 once we take the limit. Which means we can take the L'Hopital's rule of all 4 of them, which is what we're going to do now. All right, so let's look at these. Example 1A. It says the limit as x approaches 0 of 3x minus sine x over x. We get 0/0. So using L'Hopital's, rule, we take the derivative of the top. So since it's subtraction, we take them by pieces. The derivative of 3x
It's 3.
is 3. The derivative of sine is cosine.
Cosine.
The derivative of x is 1. We take the limit again. So if we put the limit in there, cosine of 0 over 1. Well, see, we couldn't take L'Hopital's again because this is no longer 0. So we're stuck with whatever this answer gives us. Cosine of 0 is 1. So the limit is 2.
Hmm.
Yeah, it's a great rule that if you ever have the limit of a function and it goes to 0 over 0, take the L'Hopital's and no stress, no bother or anything. Just if it works, it works. If it doesn't, 0 is the solution.
Wow. That really is like a powerful method right there. Really simplifies things.
Very much. Yeah. Thanks to L'Hopital.
Yeah.
He must have been tired doing the long methods also.
You just imagine that sitting in there, no calculator or anything.
Exactly. I
But
don't
for-
have too much to do. Let me see that. Yes, again. I keep on forgetting if Okay, so we get 0 over 0. If we plug in 0 in there, we get 0 over 0. So using L'Hopital's, the bottom's going to be 1. This one disappears. So we just have to take the derivative of 1 plus x to the power 1/2. And remember, we have to keep it as the f prime over g prime. Plug in 0. Square root of 1 plus 0 is square root of 1 is 1. So it's 1/2 divided by 1. The answer is 1/2. Yeah, to answer your question earlier, I mean, think of how much more time it would take to do the quotient rule for this.
Yeah, it would be much,
It'd
much longer.
be pretty painful.
Yeah.
X goes to 0.
It almost is kind of like whenever you see some of these rules, you just know they made them for themselves almost.
Yeah, exactly.
And then they're like they shared it with everyone else, and everyone else was like, "Yeah, we're doing that from now on."
Yeah, imagine how they did it. You're right. Back in the old days, no calculators, no anything else. They had to do it by hand.
Yeah, it's I can't
Wow.
even imagine really.
Yeah, I wouldn't do that. Okay, first off, we always have to check to see if it's 0 over 0. So 1 plus 0 is 1, square root of 1 is 1. 1 minus 1 is 0. 0 over 2 is 0. So 0 over 0. So it is 0 over 0 if we plug in x equals 0. So the derivative of the square root one, we just did it earlier, so we get the same value. The derivative of 1 is 0, it disappears. Derivative of x over 2 is 1/2 over 2x. So we do each one of these separately. Since square root of 1 plus x, we just did it up here. I can just copy that over. We plug in 0, we get 1/2 minus 1/2 is 0 over 0. It's still 0 over 0. So we do it again. That one disappears. The bottom becomes 2. So we have 1 plus x to the power negative 1/2. So it's negative 1 over 2 It's going to be 1 plus x times square root of 1 plus x. Yeah, because the denominator is no longer 0, we have to keep whatever this answer is going to be. Put it in 0 in place of x, so it's 1. Square root of 1 plus 0 is also 1. So it's on top, it's negative 1/4 over 2. The answer is negative 1/8. We'll do D on the next one, on the next page. So again, you just have to make sure you know how to do the derivatives of these functions. 1/2 is a constant, so all you have to do is 1 over radical 1 plus x. So that one goes in here, which then comes back here. Let's look at D. The limit as x approaches 0 of x minus sine x over x cubed x 0. Sine of 0 is 0, so it's 0 on top, 0 on the bottom. So the bottom, 3x squared. Derivative of x is 1. Derivative of sine is cosine. It's still 0 over 0. The 1 disappears. The derivative of cosine is negative sine, so the negatives cancel. So the bottom becomes 6x. Still becomes 0 over 0. But because the bottom now becomes a constant, so derivative of sine is cosine. Cosine of 0 is 1. Over 6.
And then we just get our limit. Don't even have to do anything else.
That's it. Yeah.
That's really nice.
Yeah, it's L'Hopital's rule is always been my favorite rule in calculus because the simplicity of it is beautiful.
It is, yeah. I mean, and it requires effectively no kind of memorization.
Exactly,
I
like the
mean,
quotient rule.
yeah, really. I mean, with the fish method, you don't really need to memorize anything. You just you know that it works and you know why it works, and so you
Mhm.
just apply it.
But the only reason we can't do this only works if it's 0/0.
Right.
Yeah, if that doesn't work, then we have to use the quotient rule.
But this is a good first, try.
Exactly. Yes. Yeah. As I said, when you first get a function, plug in the limit value and see what you get. If it's a number, you're done. You don't have to go any further. If it's 0/0, you're done. You just take the L'Hopital's rule. But if it's not, if it's something different, then we have to use the rules.
And you told us that back in the beginning of the semester, so it was all leading up to this.
And yes, now you see how beautiful it is. Okay, let's look at number 2. Be careful to apply L'Hopital's rule correctly in this equation. 1 minus cosine x over 1 plus x squared. Okay, let me write that down. Limit as x approaches 0. All right, so first off, plug in 0. 1 minus 1, 0, 0. So it's 0/0. So we take L'Hopital's rule. Since they're all addition and subtraction, we take each one separately. So derivative of 1 is 0. Negative cosine. So derivative of cosine is negative sine. So the negative and the negative will cancel. 1 plus 2x. Now, this is going to give us positive sine 1 plus 2x. If we plug in 0, we get 0/1. It's not 0/0. So what do we do?
You use the quotient rule. You take the next derivative.
Yeah, yes.
Because
But we
it's
know good.
Is it because it's part of, is it because it's technically one of the forms of like infinity over 0, or
Actually, no. We can't, because it's 0. If it was 0/infinity or infinity over 0, we can go on further. But since it's 0/1, we're saying the derivative is 0. The limit of this function is 0.
okay. Because it's not undefined.
Right, because the denominator is not 0. Well, if it was 0 on the bottom, that means it's going to infinity. Yeah, it's indeterminate. But in other words, if we had 4/0, it's actually going to infinity. That's why they say it's undefined. But this infinity is not defined. So that's very important. So when you get as far as you can go, once you get to that point, it is what it is.
It's just 0.
Yeah, because I wouldn't want to do L'Hopital's. I mean, with the quotient rule with this, because it's just going to give us a big old ugly number.
Yeah.
It will not be
still
fun.
be the same thing.
Right. Yeah. It'll give us the same thing. Nothing.
With a whole a whole lot of work for nothing.
Okay, here's number 3. In this example, one-sided limits are different. So as x approaches 0 from the right and x approaches 0 from the left, let's look at their limits. It's sine x over x squared, both of them, going from both directions. The limit as x approaches 0 from the right, sine x over x squared. X approaches 0 from the left. Okay, this one is not as hard as it seems. We could use L'Hopital's rule, and I'll show you do it both ways. We could do it both ways. Right now it's 0 over 0. If I use L'Hopital's rule, derivative of sine is cosine, and over 2x. It's still 0 over 0. No, it's 1 over 0. So that means it's going to infinity. Of course, cosine of 0 is 1 over 0. So this is 1 over 0, which is infinity. Since we're coming in from the right, it's a positive infinity. Likewise, limit as x approaches 0 from the left of cosine x to x. This is 1 over 0, which makes it going to negative infinity because it's coming in from the left. If I put a negative number in place of x, I get 2 times the negative number, which makes the whole number negative. But there's another way. We could have done this particular one, we could have done another way with a rule that we learned in chapter 1. Example 3, version B. X approaches 0 from the left. So what we could have done is rewrite this equation. Remember from chapter 1, whenever we have the limit x goes to 0 of sine x over x, what does that become?
1.
Yeah. So what we really have is this formula. So as this function here, if we get close to 0, from the positive side, it goes to infinity. And this one goes to negative infinity from the left side. This graph looks like this. This is the function 1 over x. So we could have done it either way, whatever's easiest for us to do.
And so in this one, we're just using that identity
Yes.
of 1, right? Okay.
Yeah, sine x over x. Because if we can, that's the hardest part about this. We have so many identities that we can choose from. It's just recognizing where it goes.
Okay.
All right.
Mhm.
Let's look at example 4. These are now going to be in forms of infinity over infinity, infinity times 0, or infinity minus infinity. These next few examples are going to be of that form. So we can either infinity over infinity, infinity times 0, or infinity minus infinity. These are all indeterminate because just the way they're behaved. So here's example 4. We're going to be using those 4 possibilities here. So here's example 4. So we have the limit as x approaches pi over 2 of secant x 1 plus tangent. Secant is 1 over cosine. Cosine at pi over 2 is 0, so it's 1 over 0 on top, which is infinity. Tangent is sine over cosine. Sine at pi over 2 is 1. Cosine is 0, so it's 1 plus infinity, makes it infinity. So this is infinity over infinity. Which is indeterminate.
So
So we
use
can the L'Hopital's, right? We can, yeah, you're going to say we can use L'Hopital's. Very good. Yes. So what was the derivative of secant? Remember, we can use our cheat sheets here because,
it's a secant tangent.
right, secant x tangent x. And the derivative of 1 plus tangent?
Secant squared.
Which, when we simplify this secant and one of those disappears, so we have tangent x secant x. Tangent is sine over cosine. Secant is 1 over cosine. So take the top, leave it alone, flip the bottom. So we're just left with limit as x approaches pi over 2 of sine x, which is 1. That was A. Now let's get B, C next. The limit as x approaches infinity, natural log of x over 2 radical x. Ln at infinity is infinity. 2 times the square root of infinity is still infinity. So it's indeterminate. It's infinity over infinity. Okay. So now we can take the derivative of it. as x approaches infinity, the derivative of the top is 1 over x. It's dx over x. And of the bottom, 2, so square root of x equals x to the power 1/2, which is 1/2 negative 1/2. So it's
1 over 2 root x.
2 radical x, right? So the 2's cancel. So we have 1 over x, 1 over radical x.
So it's 0 over 0.
Well, let's see. We get 1 over x times the flip of the bottom over 1. So this is 1/2, this is 1. So we got 1 over square root of x. Whereas this is x squared, this is 1 sugar. No, this is x to the first. So both of these can cancel, which leaves us 1 over radical x. Because think what we have here. X is the same thing as radical x times radical x, right?
Right.
So that means one of these cancel with that one. So we just have that.
Okay.
Since the top is no longer 0, as it goes to infinity, the answer is 0.
Okay.
And C, the limit as x approaches infinity of e to the x over x squared. E to the x is infinity, infinity squared is infinity. So we can use L'Hopital's rule again. Derivative of e to the x is e to the x. Still going to give us infinity over infinity. E to the x over 2, which is infinity over 2, which is infinity.
So our limit is unbounded.
Yes, as it goes to infinity.
It's an infinite limit.
Right. Well, we knew it was going to happen because the denominator eventually is going to disappear. This
Right.
is a constantly repetitive function, so it's always going to be that.
Okay.
All right, now let's look at example 5. Now we're going to look at indeterminate forms that look like these. The limit as x approaches infinity of x sine 1 over x. So what do we do with that?
You got to use the product rule.
Yeah, because sine was 1 over infinity as x goes to infinity. This becomes 0. Sine of 0 is 0. Infinity times 0. So we got to, this is infinity times 0. So we take the L'Hopital's again. actually see what's going to happen with this one, because we may have to use something else. The derivative of sine u. It's going to be cosine u du. Du would be negative x, well, negative 2. So negative 1 over x squared. But we have a problem there because it's not what we have here. So it's going to be 1 times this. Well, actually, no, we have to do a product rule here. If you take the derivative of it. So the easiest way to do this one is by using our substitution, what we're doing here.
Okay.
So what would this one be? If u equals 1 over x, then what is x? Solve for x. Multiply both sides and divide by u. So x is equal to 1 over u. So this would be 1 over u times sine of u. Why is this one a little bit better? Because it just hit me. What is sine x over x?
1. Okay. Could we also, I mean, so there's obviously multiple ways to do this. Could you also use the fact that sine 1 over x equals inverse cosecant x? Could that identity work? I mean, that would probably be more work, but
Yeah, I'm thinking was then taking the derivative of that. Yeah, that would be a lot. But then we still have this part here.
and so then you would have to use the product rule as well, yeah.
Exactly. Yeah. So it'll just be a lot more painful because then we have to take derivative of sine, then we have to take derivative of this one. Yeah, that would just be painful. So that's why in this example it was easy when I put this together here. I saw that this is exactly what we have here. So, but if it was cosine, then it would be pretty much ruined.
Mm-hmm. Okay, so in this case, you're using a u substitution.
Right. Yeah, because now, as we did here, because as x goes to infinity, that means what happens to u? This one should have been u goes to 0. Since I did a substitution, so a change of operations, I'm no longer using x's, so I can't use this. I have to now switch everything over to u. So as x was going to infinity, u is going to 0. So that means my u goes to 0.
Okay, I see.
Okay. That's pretty important.
That's probably the best way to do that one, I think.
Yes. Because once I put that in there, because I hate dealing with fractions in this part,
Mm-hmm.
then it just hit me. Let's look at B. What is 5b? The limit as x approaches 0 from the right of radical x ln x. Because if you think about it, okay, the ln function looks like this. I mean, the radical, this is radical x. ln looks like this. So as we're coming in from the right, this one goes to 0. And this one goes to negative infinity. So it's indeterminate in that realm. So we gotta do L'Hopital's rule. But again, we can't do it right here, present it's a product rule. Because remember, we have to have a rational equation. It's gotta be irrational. It's gotta be f of x over g of x.
Okay.
So this one here we can't change. This one here we can. How do we put this function on the bottom here? If we just put this on the bottom here, right now it's
So we would take it. Yeah, okay.
like that, yeah. So now we have a rational expression. Why do we do that? Because now when we have a fraction, we can do f prime over g prime now. If not, then we have to use the product rule, and we don't want to use that. We're trying to use L'Hopital's rule. So the derivative of ln x is 1 over x. The derivative of 1 over x to the power 1/2 becomes negative 1/2 x to the power negative 3/2, which becomes negative 1 to x square root of x. Okay, so we're now at 0 over 0. But let's rewrite this, see what we have. We have 1 over x. The flip of this one, which is 2x radical x over 1. The x's cancel. So we can't do L'Hopital's rule again. Because this operation here, when we simplify it, becomes this. And since it's over 1, we can't do L'Hopital's rule again, so we just plug in 0, and we get 0.
And then that's our limit.
Yeah, because that's a valid answer.
Right.
What was that? That was example 5. Now we're going to do example 6. Here is example 6. We're going to do another one with the infinity minus infinity. Another indeterminate format. So limit of 1 over sine minus 1 over x. The limit as x approaches 0 of 1 over sine x, 1 over x. 1 over 0 minus 1 over 0 is 0 minus infinity and minus infinity. So we're good to go. So how would we do this one?
Well, the limit of 1 over sine x, we'd have to use the quotient rule for that, right?
We could, but we have two functions. Let's go ahead and put them together and see what happens there.
Yeah, I see.
Because it may things may cancel out that way.
Finding a common denominator.
Right. Because if we do this, we're going to keep on getting larger equations. Eventually, we have to combine them. So let's go and combine them right now. So this one needs an x over x. This one needs a sine over sine. So it's x minus sine x over x sine x. And if we plug in 0, 0 minus 0 is 0, 0 times 0. So now we have 0 over 0. Which means we can now use L'Hopital's rule. Worst case scenario, if this doesn't get much easier, then we'll go back to what you said earlier and do the quotient rule on both of those. Yeah, but see, if we do that, then these values just get bigger on the bottom.
Right.
X squared goes to 0, still gonna be x squared. So it's still gonna be indeterminate.
So sometimes it's better to just get the common denominator.
Yeah, sometimes, yeah, again, we have to try a method and see if it works. If it works, great. If not, then oh well, we'll try something else.
Mhm.
So the derivative of the top is derivative of x is 1. Derivative of sine is cosine. Okay, we couldn't avoid it much longer. We have a product rule. X sine x 1 cosine. So it's sine x plus x cosine x. And that's still going to give us 0 over 0. So we do it again. On top, this one disappears, so this becomes negative derivative of negative cosine is just sine.
Um,
And
I had a question real quick. For the
yes,
top one, for x minus sine x, are we not taking the derivative of negative sine x?
well, here,
Oh,
or are
the
they
one
forgetting about it?
right here.
Well, we are, because the derivative of negative sine is negative cosine. The
Oh, okay.
derivative of
So,
negative
okay.
cosine is negative negative sine.
Okay, I see. I see. Because I just thought that they would cancel, but yeah, that makes more sense.
So let's see, now we have on the bottom, the derivative of sine is cosine plus x cosine. So x cosine which becomes cosine x minus x sine x. So we have 2 cosine x's minus x sine x. Now, if we plug in 0, we got a 0 on top. 2 times 1 minus 0. So our answer is all that for nothing. That really sucks.
As usual.
Yeah, all that for 0. But yeah, eventually we couldn't run out. So the question then would be, as you were saying, what if we did the quotient? Well, because then we'd have sine times 0 minus, well, we still have 0 there because look at if we did the quotient rule here, we have 1 sine x, 0 cosine.
Right.
So we would have negative cosine over sine squared negative x over x squared cancel out one of the x's here. So we have negative cosine plus 1 over sine squared. Ooh, we have to combine the denominators anyway. Then we have a much larger one. So no, this is the easier way of doing it.
They just make it a lot harder.
Yeah, because we have to deal with a lot of squared terms on both top and bottom.
Okay.
Indeterminate powers. Limits that lead to indeterminate forms, 1 to infinity, 0 to 0, infinity to 0, can sometimes be handled by taking the logarithm of the function. We use L'Hopital's to find the limit of the logarithmic equation. So here's what we have. If the limit as x goes to a of ln f of x, then we take the if this is ln f of x, then we take the e, so it becomes f of x, e ln f of x. Okay. So let's look at this. Example 7. Apply L'Hopital's rule to show that the limit as x approaches 0 from the right of 1 plus x 1 over x is equal to e. Equal to e. Okay, let's see this. Our rule tells us to do what? Take the e of both sides. So if we take the limit as x approaches 0 from the right, and this would become 1 over x. What does that rule tell us? So it tells us the limit of ln f of x is equal to L. Then the limit of f of x is equal to the limit of e ln f of x is equal to the e L. Here's the limit. So e to the e, got that? E ln, so it's ln. Okay, yeah. So that's what we have here. Because we had to the power 1/2, 1 over x, and that comes out in front. So we got the limit as x approaches 0 from the right of 1 over x. E ln cancel, so we just have 1 plus x is equal to e to the L. The L is e, so it's e to the e. Here's the ln function. We take the ln of this now. Let me redo this again. So we take the ln of this. Limit as x approaches 0 from the right. So we take the ln of 1 plus x to the power 1 over x. Ln of e. Oh, this is 1 over x. Which means this comes out in front. It's an exponent. So we have limit as x approaches 0 from the right of ln 1 plus x over x, that 1 over x here, equals 1. As well, this has to go here. So an x goes to 0. So its limit 1 is 0. ln 1 is 0 over 0. So I take a derivative again. The derivative of ln 1 plus x is ln u is 1 over u du, which is just 1 over 1. Now we can take the when x is 0. So we just have 1 over 1 plus x. It equals to 1. When x is 0, this one disappears. So we have 1 over 1 equals 1. And that proves that this equation equals e.
Okay. I see.
Yeah, because
So
we started off with this, and we followed the formula it told us to follow. The limit of ln f of x equals L. The limit of f of x equals the ln of e to the power ln f of x equals e to the power
okay.
of the limit, which is what we have here. So ln e is 1. So that works. It wasn't really a solve. It was more or less to show that. Yeah, that's what it's, yeah. It's a show that this equals that.
So is that basically like proving it?
A proof, yeah.
Okay.
Because notice how number 8 is saying find this. This one's just saying show that. So this is a proof. This is an actual calculation.
Okay.
So in example 8, we have find the limit as x approaches infinity of x to the power 1 over x. Remember, the indeterminate powers, this is x to the power 0 or 0 to the power 0. As x goes to infinity, well, this is infinity to the power 0. 1 over x goes to 0, x goes to infinity, so it's infinity over 0, or infinity to the power 0. So if that's the case, then we have to use the same rule. It says if the limit as x approaches a of ln f of x equals L, then the limit as x approaches a of f of x equals the limit of e to the power ln f of x as x approaches a equals e to the power l. So we have to use all this here. Because our form is infinity to the power 0, that means we have to use this formula. It's an indeterminate form of that. So this is our f of x. That's our f of x. So anywhere I see an f of x, that's x to the power 1 over x. The limit as x approaches infinity of ln x to the power 1 over x is equal to, that's what it's find. So this is the same thing as the limit as x approaches infinity, the limit of ln 1, so the 1 over x comes out in front. It's a power. So now we have the traditional L'Hopital's rule of ln x over x. So we have infinity over infinity. Which means we can use L'Hopital's rule. Take the derivative of ln x, which is 1 over x, derivative over 1, which gives us the limit as x approaches 0 of 1 over x over 1. It's got to be a fraction. So this one, 1 over infinity, not 0. So 1 over infinity is 0 over 1, which is 0. This is our limit, L. So that says that the limit as x approaches infinity of x to the power 1 over x is equal to e to the power L, which is e to the power 0, which is 1.
Okay, so in this, yeah, we actually did find it. Okay, it's 1.
Yeah. Okay. All right, so that does it for that section. Now let's look at the next section. Section 6. Section 6 deals with application problems, I believe. Yeah, so here's read the problem, draw a picture, introduce the variables, write an equation. It's the same as any word problem we did in algebra. All right, so let's first start off with there's example one. An open box is to be made by cutting small congruent squares from the corners of a 12 by 12 sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So what kind of question is this looking at? What kind of equation is this looking at?
Like what kind of equation do you need to use to model it?
It starts with an O. It's an optimization problem. I'm sorry, I should have been more clear about that. This is an optimization problem. So this is going to be applications or optimization. So example one. So we have it. They drew the picture for us. 12 by 12 sheet of tin. We want equal corners to be cut out. So these are all going to be the same size. So is this going to be an area or a volume or a perimeter or what kind of equation? Problem?
It's gonna be area.
No.
If you're trying to find the
Because remember, we're going to fold up the sides.
mhm.
So we're going to have this something that looks like this.
So it's volume.
It's volume, right? It's going to be X units high, and both of these are going to be the same. So what are the dimensions going to be of the sides here? We know it's going to be X inches high because that's what we cut out on the sides. So what are the lengths of the two sides going to be?
12 inches.
Well, it's 12 inches, but we cut out an X here and an X here.
Okay.
So it's going to be 12 minus 2x, 2x. Whatever the size of the X is, it's going to be the same over here also. So our volume is length times width times height. X times 12 minus 2x times 12 minus 2x. But we're looking for an optimization, a maximum volume problem. So multiply these two together. 144 x minus 24x plus 4x squared. 4x squared minus 48x plus 144. And then distribute that. So our volume is going to be 4x cubed, 48x squared okay. That's our formula for the volume. What's going to be our domain? How big is the largest X we can cut?
6.
Right, because we have to cut here and here. So our x's have to be between those two bounds.
Okay.
Less than, it's going to be a closed interval. Now,
And
for
find
optimization, what do we have to do?
find the derivative
Why the derivative?
because you're trying to find the basically you're trying to find the minima or maxima.
Exactly. Very good. I couldn't put it a better way. Exactly. So we're going to find the first derivative, 12x squared minus 96x plus 144. They all have a 12 in common. Ninety-six divided by 12 is 8. 144 divided by 12 is 12. Okay, it's going to be XX, so both going to be the same sign, so both going to be minus. What times what is 12? When we add them, we get 8. 6 and 2.
So we have that
Right. So now
6 and x.
when we find the first derivative, critical values when the first derivative set equals 0. So here we have x equals 2 and x equals 6. Those are our critical values. So can we use x being 6?
No.
No, because if we use x equals 6, that means we just fold it in half. So we can use this value, x equals 2. And remember, our domain, we have to also try the n values.
And so that's another reason you can't use x equals 6 is because you're going to use it anyway.
Right. Yeah, because we always have to try the endpoints. Remember we did last chapter when we talk about maximum minima?
Right.
You always have to try the endpoints and the point in the middle. The first derivative set equal to 0. So because now we're looking for maxima and minima, as you said earlier. So now we found the is this the absolute maxima? Well, we also have to test it against the other two. That's what we're looking for. Since we're looking for the maxima, we try all of these points. And here's the function we're going to be using. It's easier if we use the factored form. So if we put x is 0, then we have -6 times -2. No, not the derivatives. Oops. Not the derivatives. We have to use our volume since we're looking for the volume. I'm sorry.
So that one is 0, the first one.
Let's see. Well, no, because if this was correct, I looked at the wrong formula. We have to use since we're looking for the maximum of the volume, we have to use the volume formula, not the derivative like I used, but the derivative of the function itself. So if we plugged in 0 inside here, it's going to be 0. If we plugged in 2, we'll have 4 times 8 minus 48 times 4 plus 144 times 2. 32 minus 192 plus 288. So 288 plus 32. Well, it's 288 plus 32 is 320. Right. Minus 192. So it's 8, 2, 128. Yeah. And then we put 6 in there. We got 4 times 6 cubed minus 48 times 6 squared plus 144 times 6. What's that? 2 cubed is 8. 6 times 6 is 36. 216.
That's going to be 0 also.
It's gonna be 0.
Yeah, that one's going to be 0.
Okay, so yeah. So the minimum is 0. That's at 0 and 6, the endpoints. So the graph will look something like this. At 2, so the squares being 2 inches each, which means our base will be 8 by 8 and 2 inches high.
So the way that you can the way that you can optimally cut corners off of it to get the most volume is with 2 inches.
In this case, yeah, with a 12 by
Okay.
12 sheet, right? If it
Okay.
was 10 by 10, it would change because of that.
That's really cool. Yeah.
Yeah, actually, and you're right. The first derivative is to find the maxima or minima, but we always, after we get the maximum minimum points and the end points, we have to try it back at the original function.
And that's to make sure that it's between those two values.
Well, we're looking for the highest, largest number, because the
Right.
largest number could happen at the end points.
Okay.
Okay, now we have another application problem. You've been asked to design a 1 liter can shaped like a right cylindrical cylinder, circular cylinder. What dimensions will use the least material? So now we're looking for a minimum. So what formula would we use for this one? Are we looking for area, volume, perimeter, or what?
We're looking for surface area. Because the material is not, it's hollow.
Right. Yes, because it's a cylinder, it's a circular cylinder. Exactly. So we're going to be using an area, base times height. And we're looking for the surface area. So we have to find the area of the top, the area of the bottom, and the area of the can itself. So we have to do the top and bottom and the sides. So what's the formula for a circle?
Pi r squared.
Yeah, area for a circle is pi r squared. We have two of them, so we have 2 pi r squared. And now we're looking for the circumference because we want to know the outside dimension of this thing. So we take the derivative of this. 2 pi r squared, 2 pi r, oh, times the height. Duh, we haven't taken that into consideration. Yeah. Why isn't it squared? Because this is the entire circle. We only want the circumference
Okay.
times the height. This is our formula we'll be using.
And uh, so we're adding that 2 pi r on because that 2 pi rh, because that's going to give us the,
This is the side. This is the circumference of the side
okay.
because we have the lid and the base. That's what this one is. The 2 pi r squares. And we have the 2 pi r h. That's the sheet that's going to fold to make the side of the can.
Okay.
So now we want to find the minimum material. Well, it seems like we're missing something. Ah, a 1 liter can.
Mm.
How much material is in a 1 liter can?
What was that? You said how much is in a 1 liter can?
Yeah.
Like how many ounces?
Well, because we want dimensions, so it's got to be in something like. So, how much is the volume inside there?
Okay.
Because we have to set it equal to something, so it's got to hold that much. What? Let me see. That's what I found it. 1 liter equals 1,000 cubic centimeters. There's the conversion.
Okay.
Yeah, because it's got to be a 1 liter can because the volume dictates how big it's going to be.
It also says that H equals 2R. So can we
Well,
substitute 2R
that's what
for
this thing says. This is we're gonna look at what this means later on because
okay.
1 liter can uses the least amount when 2R. So this is probably the answer. We'll see about getting there. So this is the top and bottom. So this equation 2 pi r h has got to be equal to 1,000 cubic centimeters. Pi r h. Pi r h. Because we want the volume. The volume is the radius times the height. But the area is it. I gotta see which one fits here.
Yeah, because the cubic centimeters, that's a unit of volume still. Because
Right.
that's the same as milliliters.
So we gotta look at the volume. Yeah, so we can't use the area ones. What's the volume?
The volume isn't it 2 pi r cubed or I think volume of a cylinder. It's a
Because
pi
this is
r squared h.
yeah, because this is the surface area. That's the outside of the can. We need to set this up to the inside of the can.
Right. So then it would be pi r squared h.
But because here we have pi times the radius and then the height. It's this number here that I'm worried about, the 2 out in front. So it's not gonna be this, it's gonna be the volume. It can't be pi r squared h. It's got to be this for sure. I don't know about that because there's the 2.
Yeah, if it's just the volume, then it's just pi r squared h.
Yeah, so pi r squared h. That's the volume. So we have to set this equal to 1,000. So we have pi r squared h equal to 1,000 cubic centimeters. Yeah, because we're looking for the internal volume of it. So that's the inside. And the outside is what we had earlier. 2 pi r squared 2 pi r h.
And then we have a system of equations here. Is that right?
Yeah, but so yeah, we have the volume. These have pi r. We just don't have h. Yeah, it's a system of equations, right? And the only thing we can't define in this one is the h, because they both have pi r's.
Mm-hmm.
So h would be 1,000 divided by pi r squared. So the pi's cancel. One of the r's cancel. So we have 2 pi r squared plus 2,000 over r. The question is looking for surface of the material.
Mm-hmm. Yeah, which will use the least amount.
That's the minimum. So we have to take the derivative eventually and find the minimum of the bounds, the endpoints. So let's take the derivative. And the only variable we have is with respect to r. Set that equal to 0 since we're looking for the minimum. Move that over there. Multiply both sides by r squared. Solve for r. So divide by 4 pi both sides. So r cubed is equal to 500 over pi.
So with that formula for the height, 1,000 cubic centimeters divided by pi r squared,
This
you're
one
just plugging that into the volume, the plus 2 pi rh.
right here. Yes, because we can't take the derivative of it if it has two unknown variables,
Okay.
which is why we had to know this, because everything has r, and that's the only thing. R is what's going to change the dimensions. The height, yes, but r is in everybody. So the h is the only thing we can solve for to eliminate that extraneous variable.
Okay.
Okay, so we have r equals to the cube root of 500 divided by pi. So that's the radius. That's going to give us the minimum.
Okay.
So we have the radius. Now we just need the height. And the height was 1,000 over pi r squared. Okay, so unfortunately, these don't cancel.
May need to use a calculator on this one.
Yeah.
I'll get the value real quick.
Yeah, so let's look at both. Let's find the radius first, then we'll square it and do all that.
Okay, well the height down there is going to be 10.8385.
10.838, 10.84. Since we're doing with centimeters.
Mm-hmm.
And what's the radius?
The radius. Oh, I messed up.
This one here, 500 divided by pi cube root.
For the radius, I got 29.37. For the R, the cube root of 500. Or never mind. I hang on one sec. I squared that. So it's actually yeah. So let me just do the square root on that. It's actually gonna be 5.42.
Okay, so this is 5.42 centimeters, and this is 10.84, which is what that picture said.
Yeah, you're like, huh? Yeah, I
That's
squared that.
that's an awfully short and wide can.
Yeah, I squared that. That was why.
Yeah, so if you look at here, then the least amount of materials happens when the height is twice the radius. And that's what this is. 2 times the radius equals the height.
Oh, okay.
So that's what it found. And we found the minimum by setting it equal to 0.
By setting oh yeah, that the 4
first
pi r
derivative,
minus
the area.
2000 over r squared.
Yeah, so the optimal thing in this one is we have to eliminate all the variables, go down to only one, so we can solve for it. That way we can solve for r. Once we find r, then we can go back up here and find the height.
And so the minimum is the 2 pi r what
Well,
was it?
both of these, because for this can, we have to have the radius of 5.42 and the height of 10.48 to find the minimum.
Okay.
So it's going to have that ratio, 2-to-1. Here's number 3. A rectangle is to be inscribed in a semicircle of radius 2. What is the largest area the rectangle can have? What are its dimensions? So a rectangle is to be inscribed in a semicircle. Of radius 2. Yeah. Okay. So this is what it's asking us. It wants us to find what is the largest area of the rectangle. It wants us to find this. That can fit into that thingy. So from here to here, we're saying the radius is 2. So what is the x? And then we have to find out what is y. So we know the radius is 2. So we'll use the a squared plus b squared equals c squared. Instead of c squared, it's r squared. So it's x squared plus y squared equals r squared. The radius is 2. So it's x squared plus y squared equals 4. Solve for y. So y is equal to the square root of 4 minus x squared. That's the y.
And then x is going to be the same thing, right? It's going to be x minus x equals 4.
4 minus y squared, right? But we'll try to limit, because now here we have this equation and we could find a derivative of that. But if we need to find a derivative of that, so we have to look at, because we need to find this.
So
the-
if we can find the derivative, we have to use implicit differentiation.
And that's what we're trying to get away from, because we can't have two variables. That's what we have to find a relationship between. I mean, we know the bound of the radius. The radius has to be between 0 and 2. Or the horizontal. X has to be between there and there. Because that's as far as it can go. But it's not going to go that far, because it's going to stop way before that. So the base. So we have the x times y So the x is x squared. The y is square root of 4 minus x squared. Not x squared, I'm sorry. Because we have this x here and this x here, so we have two x's. So the area is twice the x from 0 times our y value. And it has to be within that bound 0 to 2. So let's find the first derivative. So 2x 4 minus x squared to the power 1/2. So it's 2 x squared to the power negative 1/2 negative 2x. Those two cancel. So we have negative x over square root of 4 minus x squared. Two times square root of 4 minus x squared minus, oh, it's plus, it was a plus, I'm sorry. But it's a minus because of that. 2x times x is 2x squared over 4 minus x squared. If we set that equal to 0, move that over there. 2x squared 4 minus x squared equals 2. Multiply both sides by radical 4 minus x squared. So 2x squared equals radical that gives 4 minus x squared. Eight minus 2x squared. Four x squared equals 8. X squared equals 2. X equals plus or minus radical 2. No. Okay, so we have the x dimensions. Oh, okay, so which one can we not use?
Oh, the 2.
No, we can't use the negative because the domain is between 0 and 2, so we can't use the negative.
Oh, okay, yeah, that's right, okay.
So what we have to do is we have to check x equals 0, x equals radical 2, and x equals 2 to see who has, are we looking for the highest or lowest? Largest. We're looking for the highest. These are our critical points.
Right. So that x equals negative root 2 is actually just an extraneous solution.
Yes, the negative, yeah. Because now we have to look at only positive dimensions. So yeah, so if at x equals 0, it's 0. At a equals 2, it's 0 also. Two radical 2 times 4 minus 2. 2 radical 2 times radical 2. 2 times 2 equals 4.
So x equals √2 is going to be our optimal.
Well, it's looking for a rectangle, right? Yeah, so this is the area. It's going to be this times this. This is the base, and that's the height. So this is the y value, and this is the x value. Because at this point here, we combined them already. So here's where they're separated from the beginning.
And those are the dimensions for our answer.
Yeah, so it's 2 radical 2, and then the y is radical 2. So in our picture here, the width from 0 to is 2 radical 2 is the base, and the height is radical 2. And that'll give us the largest maximum area inside there. All right, let's look at example 4. This will be the last one because it's getting late. Here's a physics one. The speed of light depends on the medium through which it travels and is generally slower in denser media. Fermat's principle in optics states that light travels from one point to another along a path for which the time of travel is minimum. So we're looking for a minimum. Describe the path that a ray of light will follow in going from point A in a medium where speed of light is c1 to a point B in a second medium of c2. Describe the path where the speed of light travels. Okay, the time of travel is minimum, so we're looking for t. And this is a motion problem, so distance equals rate times time. So it's distance over rate. So let's see what this one's really asking us. So we have some object. Light is traveling through this median. That's median A. from point A. From a point A in a median where the speed of light is c1 to a point B once the median changes. This is at c2. Well, there's some point we're going to get to, and that's where mediums change. So time equals distance over rate. The rate is in this first one is that one. The rate in the second one is that one. The state of light travels states that light travels from one point along a path which times the minimum. Describe the path of light. Distance traveled from here to here. That's X. And we'll call this one A. This one's X, and we'll call that one B. So the distance is X squared plus Y squared equals D squared, so it's square root of X squared plus Y squared. Or since we're starting from A, it's moving along the same path. And the same thing has to happen for this one. It's got to travel from here to there. So from P to B, X squared plus B squared. All right, let's see what this gives us. So the total time, this is time one, and this is time two. The total time through both median is it has to travel that distance plus the minimum. So we're going to take the first derivative of it. Oh, no. So let's take the derivative of both of these separately. That's a constant. So X squared plus A squared to the power 1/2. 1/2 x squared plus a squared negative 1/2 times 2x. Which is 2 over square root of x squared plus a squared. This can't be the same x. I can't have the same x's here because the distance
Oh.
traveled,
Yeah.
because if the distance traveled here is this is if this is distance x, and this is the distance, so this is the distance minus x. To get to b, so this one is distance minus x. Oh my God, it's gonna be much larger now. So the second one's gonna be distance minus x squared plus b squared over nothing. So it's gonna be makes it 1/2 times the derivative of the inside, which is this one. Times -1. So that becomes 2 -2 distance minus x all over 1/2 that's that much. So the 2's cancel. So it's going to be distance minus x square root of distance minus x squared plus b squared. There's an x there. The 2's cancel. This 2 and that 2 cancel. So it's simply x over there. Yeah. So there's our derivative.
Yeah.
Holy smokes.
Yeah.
Now
And this is why we don't do physics.
we're looking for time travel is a minimum. So we don't have to worry about the bottom. All we do is worry about the top. X plus d minus x. So we need no d is 0. Crikey. No, we have it's not really that so easy. Because I first have to get a common denominator. Won't be that easy.
Yeah, so we have to do what?
We have to multiply this
Yeah.
to that,
Times that.
this to that.
and then get our common denominator.
Well, yeah, because once we say that equals 0, the bottom all disappears because we multiply by the LCD and that gets rid of it.
Right.
And we just have x times all of this, d minus x equals all this. Holy smokes. I don't want to do that. No. Since it's moving vertically and horizontally. No. Yeah, I mean, we could. There's some other things we can try, but no. Okay.
To be continued, yeah.
Yeah, to be continued later.
I think that is a good plan. That's a
There's-
long problem because
That's a lot.
you're dealing with the speed of light in that one. So
Yeah, and there's two of them because the speed changes through the medium. So it's no longer just a constant speed of light. It's a different speed of light.
yeah, with two different distances for each median.
Right.
Because that's like when you said, "Oh my God, that's gonna make it even bigger." Yeah, with the d minus x.
Yep. Is now when we have all these cross multiplications. Okay, let's look at the last two. These are the ones we did earlier also. It has to do with economics. Remember economics, we had R for revenue, C for cost, and P was revenue minus cost is profit.
Right.
And we talked about marginal cost, marginal profit, marginal revenue.
Mm-hmm.
So the marginals were the derivatives. Whenever you talk about marginals, you're talking about derivatives. So that's what we're looking here. Let's look at example 5. Suppose that the revenue is 9x, the cost is x cubed minus 6x squared plus 15x, where x is the millions of MP3 players. Is there a production level that maximizes the profit? If so, what is it? Okay, example 5. This will be the last one because the other ones will be pretty much the same thing. The revenue equals 9x. Cost is x cubed minus 6x squared plus 15x. Is there a production level? So we're looking for production, which is revenue minus cost. Where's that? Oh, well. So we're looking at to maximize profits. So we're looking for marginal profit. So we have to take the derivative. So R prime will be 9. C prime 3x squared minus 12x plus 15. Well, since we're looking for a maxima, we have to set it equal to 0. So we have R prime minus C prime, which makes it R prime equals C prime. Subtract 9 from both sides. 3x squared minus 12x plus 6. Factor out a 3. Which means now that we can't factor it, because what times what is 2 when you add them, you get 4? Nothing. So we got to use Pythagorean theorem. With A, well, let's do it from usual. A equals 3, B equals negative 12, and C equals 6. So negative of a negative 12 plus or minus negative 12 squared, 4A times C over 2A. Well, plus or minus 72 over 6. No, in order to cancel this, you have to have both of them on top, since it's addition, subtraction. So we take 72. 72 is made up of 6 times 12, which is 6 times 2. So the 6 comes out radical 2. So I can factor out a 6. So my x is equal to 2 plus or minus radical 2. And what was the last thing for? Maximize profit. So we have put it back into our 9x minus x cubed plus 6x minus 15x. Negative x cubed plus 6x squared minus 6x. Because it's a negative, we know it's a decreasing function. So the maximum will occur here. And that will be this is the 2 plus radical 2. This is 2 minus radical 2. So we plug in the value into our equation and see what we get. We plug in both of these into this equation and see what we get. Actually, not this one, this one. One for 2 plus radical 2, one for 2 minus radical 2, and see which one gives us the highest. clearly concavity. No, we need to, we know it's. Negative 3x squared plus 12x minus 6. We did that. Yeah, so this will give us, since it's backwards, this will give us the max and this will give us the min. Yeah, so because it's a negative function, because the cost is a larger function, it's an x cubed. Yeah, it goes down, so when we put in the 2 minus radical 2, it'll be flipped. So this will be the max and this will be the min, once we plug it in there, because it's backwards. Yeah, this section is not going to be a lot of fun because
Yeah, not
simply
for the problem,
because
thing.
I know. It's because simply because all the formulas you have to know. And that's what really sucks, because in business they have their own formulas for everything. As you the marginal cost, revenue, profit. So wow, it just will be a lot of work. But for us to find the derivative, we have to set them equal, because set it equal to 0, and then set r equal to c, r prime to c prime, and then solve it from there. Which is the same thing we got earlier. It's just that we had a negative coefficient because it's the inverse function. So the smaller value will give you a maximum, the higher value will get the minimum. So that's going to be the maximum at x minus radical 2. You just plug those back into the revenue and the cost. It'll tell you how many of each will give you to maximize it. Okie doke. I'm sorry, but I kept you all way too long. I'm sorry.